Ready to start. Welcome back, everybody. We have next lecture, lecture 7. So today we'll talk a little bit more about planning, but you will see that the topic is going to change a little bit, right? So we are going to be talking about decision-theoretic planning. And, well, this is mostly related to decision making. And also very related to this topic are games. Games against nature, probabilistic, and all these things, okay? So, yes, let's get into it. For this, reference is Russell and Norvin book. There's other extra readings that we will upload to Canvas, right? But the topic, as I said, has changed a little bit. We're going to discuss, or we're going to present what decision-making means, right? So all of us with decisions, come in class, take notes, very simple things, but we need a little bit to formalize this idea. We will define what means a plan against nature. So we are going to define what nature means now, and then we'll see like a couple of variants, right? First one is non-deterministic, and then there's the probabilistic way. Later we'll define sequential decision making, Minimax, search trees, and then these two very famous algorithms for solving games. The first one is Alphabeta Pruning. I'm just going to present it briefly later, but this is something that has been used a lot for solving Minimax games on trees. And the second one is very famous, and we are going to spend a little bit more talking about this, which is Monte-Carlo tree search. Who heard before about Monte-Carlo tree search? Oh, okay, very good, very good. Can you implement it now? If I give you, okay, you will be able to do this after this class. Okay, you will, if you spend enough time. Actually, I have to say that this was problem set 4, or it was supposed to be problem set 4, but I'm going to leave this optional. So we will release just the document or the instructions if you want to follow them, but this was supposed to be problem set 4. Okay, we'll talk more when we get here, but let's start with basics, right? Let's start just by defining the problem properly, and we'll see what we mean now by plan, or now in this case, we are going to change, and instead of talking about plans, we will talk about games. Okay? So let's consider two decision makers. Decision makers, this is nothing new. We have already, most of the time, used the word agent or the word robot before, some entity that has some actions, right? So in this case now it's just this, someone taking actions, and then we'll see how it looks like. Okay, so for the robot it's clear. We know what it is. Decisions means sometimes moving your mechanism, moving in this workspace where there's obstacles living and you want to avoid collisions, you want to get to the point. Let's say it here that there's not really a game going on, right? Let's say that it was mostly deterministic spaces where we knew where the objects were, we knew where the robot was, so we knew their state. And planning was just more a problem of, if there's a solution, we want to find it, right? So that was a little more straightforward. Now what we are going to add here, and this is just a motivation, I'm sure that, well, you will see later that, oh, but this is what they meant by nature. We add a second decision maker into the formula, okay? And this decision maker we are going to call nature. So what is nature, right? I'm not talking about, well, biology, but I'm talking about nature as this kind of mysterious and unpredictable entity, right, that is going to affect the result of our plan or of our decision making. Well, I'm here saying for the robot, but it could be for any other agent. So it's basically everything that is beyond our control, right? all these processes that we cannot directly control, or we don't have access to, or we don't know they are noisy. Some people just call this noise, but we will start with this as a decision-making agent, someone that is just taking, but it's simply taking actions, but we don't know what they are. They are unpredictable. Okay, so it's a different way of looking at the problem. Yes, as I said, this is going to interfere with the main decision maker. And then basically to achieve our goals, now we need to deal with this uncertainty. Okay, so let me give a couple of examples. Let me start with the problem that we had before with the robot. Can anyone propose here a state variable? No? Okay. No, sorry. So we call these configurations, right? It could be a two-dimensional pose, right? So let's say that only with position and orientation would be enough. Okay, well, we have here our configuration, and then let's say that here we have some obstacles, right? And because of the nature of these obstacles, well, there might be not perfectly known. Okay, so in this case we can consider this as a problem of robot versus nature, right? In this case, nature is like this domain that we are not sure. These obstacles, maybe they are trees or they are something there. We don't know for sure. Maybe we don't know here. Maybe we need to get closer. But basically what we want is just to plan here. So this is maybe part of this nature could be also here we have a system that is not exempt of noise, so you execute something and sometimes it's not exactly as you thought it's going to be, so action results and action commands are usually not the same. Imagine here you have some obstacle, like, well, small one, let's say a rock, and then things perturb a little bit, right? So this is also part of this nature. We could say some agent is putting that rock there for our robot not to move as we thought. Okay, this adds uncertainty. The world is uncertain, by the way. Another more abstract thing, right? Imagine you are now in Moscow, November, and then your decision making is, should I take the umbrella or not? Right? So then you need to think, okay, doesn't look very good. Maybe there's going to be rain, maybe not. You consider something, in which case it's going to be your cost, whatever it is, right? So we don't really formalize this in numbers, but we somehow have like this notion of cost. And then, well, let's say that at the end you will see. Maybe you carry your umbrella all day and nothing happens, or maybe there's rain and then you are very happy that you took this, right? So here, who is the agent? It will be us. And who is nature? So nature is this random process that is making rain fall or not, okay? So let me put it this way. Rain, so this is nature, and in this case this is decision making, us. Okay, you get the idea. I'm sure that you have discussed about randomness in many other courses before, right? But let's just start this with with the very first definitions, because then later this is going to affect a little bit how we do planning or how we play games. Okay, so if now we agree that we have these two entities or these two decision makers, we can do two kind of distinctions. Okay, so the first one would be, I mean, distinctions means like how are these games going to be played, or how are these plans going to look like. What we have now is, well, this is the usual action space that we are used to talk about, right? There's always action space. But we have now is a second action space that belongs to nature. And this could be limited maybe to rain, or it could be any other thing. But depending on the problem, it could be actually much more involved, and it could have like deeper consequences. The other component that we need is a reward function, right? So what we have here is this pair of actions from the robot and from nature, and as a result we get a value, right? This could be good or this could be bad. And this is what we need to see, right? Maybe nature wants best for us, and then the game is everyone just wants the best for you. Or maybe not. Or maybe it's just the opposite. Nature wants the worst for you, and you want the best in terms of maximizing this number. Okay, so these are little variants, but let's say that the ingredients, as always, because we need to define the planned problem, the ingredients, as always, involve defining this, right? So now it's just this new action space. Okay. Let's give this example, right? Because we were just thinking. So we were thinking, let's imagine that nature is helping us, right? Okay, so, and we take actions simultaneously. If you know that nature is going to help us, then which action would you take? So here you have three actions. You have U1, you have U2, and you have U3, okay? And for each of these actions in this table, we see that there's different values. And they correspond to the different actions that nature can take. Okay? So what we are doing is just discretizing the action space to give like this very simple example, but imagine that this state space could be, or this action space could be much larger. Okay. Who would choose U1? Okay, we have one U1. Okay, I didn't explain. That's true, that's true. Let me explain. Let me rephrase it. You want to maximize your reward. So let's say, I don't know what this is. Maybe this is playing guess who has the highest card or whatever other game. And then, well, with some reward. We don't know what the game is. But what we know is that we are going to take action simultaneously. Okay? So nature and you are going to take the action simultaneously. That means that you will not know what nature is playing. Okay? So I could be nature here in this game. Let's say that I'm nature. And then I'm asking you to choose one action. You have three actions. And then you don't know what's going to happen, but you know that the combination, because this is the reward, how we are defining the reward. Given an action, and given the second action from nature, there's going to be a value. So in this case, you want to maximize this. Okay? And what I'm saying is that nature wants to maximize our reward as well. And the question is, there's no right answer, right? So usually it's going to be a little bit different, and I'm going to explain later the variants. But what we want is to get the maximum number that we have in this table, if you want, right? So let's abstract but, so this is the thing. Exactly. This is the full table with all pairs of actions resulting in a reward. So we have this function totally specified. Okay? Okay, good. This is the game. I don't know what game can give like this kind of numbers. I don't know. But we were saying, who wants to take action 1? And then we had, let's say, one agent that was taking action 1. So here comes the result, okay? Nature is going to take something. It doesn't know what we have taken, right? Okay. But the important thing is that you see that if you take action 1, you're going to be probably not as good as taking other actions. Why is this? Because if you take action 1, and remember that in this game, nature doesn't know what you are going to be doing. It's just going to choose another action. It's going to be like any of these 3 results. So you either have +1, which is okay, I guess, -1, which is smaller number. So in terms of our reward, we are not so good, right? And then we have 0. Let's see what happens if we choose U2. Okay, okay, let's take this more randomly. There's no like right answer. Actually, we'll see that nature works a little bit different. And this is the first kind of discussion, how nature works, why we need to define it. But let's say that in this case, nature wants the best for us, and it's not really taking any hard decision, it's just doing, well, whatever. So for you two, what we see is that there's also 3 outcomes, and it's going to depend on what nature is choosing. Remember, nature doesn't know that we have chosen this. So it's kind of simultaneous decision. And in this case, what we have is the max value, right, is higher. So we have a higher reward. We also have a smaller reward, right, that could be -2. Imagine we choose 2 and nature for some reason chooses to this action, right? So then we'll have probably the worst outcome in the table. Worst thing that could happen, it happened, okay? And then we have another value, and the same happens for U3, right? So for U3, nature doesn't know, we don't know neither what nature is going to be taking, and then we have kind of these 3 results. Okay, so I hope that with this we understand a little bit now what we mean by a game, and this is just the simplest definition of the game. Later we'll add a little more extra things, let's say, to it, but this is just a result. Nature does something, we do something, we see the result. And now the question was, okay, what are we going to be choosing, right? So this is the decision making. If you want, it could be like something simpler, like the umbrella problem. Here, let's say that nature says that rain, no rain, and our action is take, umbrella, no take. Okay? So let's give some numbers. What is the best thing that could happen here? Just to give like another example with more things. The best thing you can do is, let's say that I'm just going to assign random numbers here, but at least we know what is bad. So this is going to be bad. It rains and you don't take the umbrella. Okay? Everyone agrees that this will be a game that we didn't play very well. There's another bad outcome. There's another bad outcome, probably not as bad, but is you take the umbrella and it doesn't rain. Okay? So let's say, again, someone could be arguing, why are you choosing this reward? I'm just choosing them for the example. It doesn't have any meaning. Okay? But you should be here thinking about this as a positive thing, right? It's like you are looking for positive rewards, means that are things that are useful for you. Okay, so you go all day with your umbrella, and it doesn't rain. Okay, it happens, right? But it's not so bad, so you can have a small umbrella. And then let's see the other positive kind of results, right? Here what we see is you take nothing and it doesn't rain. Okay, sure, it's good, maybe. And the best one is, oh, it rains and just in that moment you show the umbrella. Okay, so let's give this a high reward because you are a prepared person. Okay, so this is what a game means. Here I'm just adding more actions, but it's just another game, right? You just need to think about it. Okay, is this clear? Because we are just going to be talking about this, only this later in the class, right? It's just going to be variants of this and then, well, but the principle is this. There's like now these 2 pairs of actions and we want to do well. We don't want to get caught in rain. We don't want to take the umbrella all day, right? So this is what, decision-making means. By the way, there's no way of knowing sometimes, so this is also something we will discuss a little bit. Okay, I was saying that this is simultaneous. You take this action and you don't have any knowledge, or at least not that we know. The second one is nature knows. Okay, and this is a little bit scary, right? Because nature knows. What it means, in terms of defining the action spaces, we just take our action space, the same as before. And now, take a look at this. Okay, so now the action space for nature is conditioned by the action space that the agent is taking. right? So this is the only little difference that was from before, see? This is just action space. It's not conditioned by anything. It doesn't depend on anything you do. Now what we are saying is because nature knows, this action space is going to be changed a little bit, right? Maybe they are the same elements, but well, at least this is our way of denoting that nature knows what was the previous action. And this is basically open the discussion for sequential games. Okay, so now nature knows. And then we have a reward function formulated as before. We have a pair of numbers, and then we have this same table. And I'm going to ask you now the same question. So before it was, okay, nature, I don't know what it's going to be, could be anything. We don't know. But we were discussing, if you want best results, well, if you don't want for sure to have the worst results, this is the thing you should not be doing, choosing this action, and best results, this is the action you should be taking. Now the question is, we are going to choose first, and then nature is going to choose. So let's go over this again, right? Let's see what it means. If we choose U1, okay, let's say that now nature is going to choose worse things for us. Yes, we have a question. In this case, in this example, yes. Nature minimizes. It could be maximizing. We could be playing this game also, but let's say that this is not so interesting. Usually, well, we see that this is a non-deterministic game where there's a min-max problem. But yes, you are right. I didn't define, and nature now it's going to minimize whatever we choose. Right. So that means that we come here, we choose this action, and then from all the possible outcomes, I'm doing this because the table is small, right? Nature is just going to choose the worst for us. Okay. So we know this. That means that we choose now a second action. And we see that the result is going to be a little smaller, right? So this is worse for us. And the same for U3, right? So we basically have here 3 choices. 2 of them are the same, and 1 of them is clearly worse, right? So whatever we do, let's not choose U2. Okay, so I'm just giving intuition, right? I'm going to formalize this a little bit better because, well, but the important thing is that in this sequential part, we will be exposed, right? Whatever we do is going to be known for the next movement. And if you think about it, most of games that we play are like this, right? So on chess, you move one piece, and then the other agent moves the other piece, right? It's not that, okay, close your eyes and both players move something. No, which games are like this? Okay, well, anyway. There's other games like this, right? So it's basically a sequence. So now you understand why this second definition is important, right? Like this kind of nature knows or the other agent knows represents an important part of games. Okay. Now let's define, like, I think what is probably the most important distinction. It could be games, as we said, like simultaneously or sequential, but we need to do a distinction exactly on how nature operates. And it's going to be these 2, non-deterministic versus probabilistic models. Okay? Let's see what is the motivation for this. The question is, what is the best decision for the robot now that it is engaged in a game with nature, right? Robot, decision makers, anything, right? So it could be you. Well, the first thing is that this answer depends on the information we have, right? It's not the same as if you know how nature is modeled or how nature responds versus if you don't know anything, right? So that depends on the information that the robot has. And then what we see is that usually there are 2 models, 2 main models, 2 main reasonings behind this. Well, reality might be very different, right? But what I mean by models is that this is the most representative models for us to play these games, or at least plan over these games. Okay? The first idea is non-deterministic. So that means that you don't have any idea what nature is going to be doing, right? You don't have any idea. And it doesn't mean that this is a probabilistic approach, because there's a second probabilistic approach that it's a little more interesting, and is we have observed nature for some time. I don't know, you go to the casino, you observe numbers, maybe you see some pattern, I don't know, but you have gathered statistics, or for instance, how likely it is to rain in November in Moscow versus how likely it is to rain in, I don't know. Well, it's very likely to rain. Oh, in February, right? It doesn't rain, it just snows. So win-win. Okay, so this is very likely. Actually, yes. These are the two distinctions. We'll see that non-deterministic actually is very, very exhaustive, because we don't know. Since we don't know, we have no idea, we are going to assume the worst, right? So that's what min-max comes from. And probabilistic, we'll see how the problem gets redefined. Okay, all the other things are just going to be variants of this. We either have a probabilistic model, and this is very broad if you think about it. We gather statistics, or we have a distribution, what it means. It could be anything, right? So there's very complicated distributions. So to me, this is still very broad definition, but this one, non-deterministic, is actually very, very strong assumption, because well, I think it's going to come now. Okay. So as I said, this is a very strong assumption, and the idea behind is, since we know nothing, the only safe assumption we can do is that the worst is going to happen. Right? So I'm sure that you know someone that has this kind of mindset. You always expect for the worst. This is very exhaustive, because then at the end, sometimes when you expect for the worst, it's very complicated to have anything working. Right? It's like, no, don't get out of the door. Nature is going to make, I don't know, some hurricane just in front of you. And okay, I'm exaggerating a little bit. But basically, worst case scenarios are usually very demanding. Right? So, why is this? You can imagine that nature is kind of adversarial, right? It's just looking to do the opposite objective of whatever you are trying to achieve. In terms of reward, if you are trying to maximize your reward, nature is just trying to minimize your reward, right? So here what we have is counter objectives, right? What direction of one agent is trying to achieve is just the opposite of the other. Okay, another motivation, Murphy's Law, right? Maybe some of you have heard about it, maybe not. Well, if anything can go wrong, it will. Maybe you have a Russian saying for this? No? No, okay, yeah. What is that? Okay, yes, okay. Yeah, but Murphy's Law, very popular. So this is another motivation why you want to take this non-deterministic model. Again, this is not the most common thing, at least for modeling reality. So usually, but for games, usually it's a good approach. Why? Because you have limited state space, you have limited action space. I'm talking about limited number of elements, and you can consider worst case scenarios. If you take reality into account, the amount of things that can happen is simply enormous. Like I was saying, you can have a hurricane, or you could have a lightning, or many other things, right? So it depends a little bit also on how we can define things. And now, with this, after we are all convinced that we are following a worst-case scenario, we can now define what Minimax games are, right? So with this, we want to calculate the best reward, right? And best, remember that it's not going to be exactly overall best. It's going to be kind of compromise. You see this here, right? Although there's many better options because of nature of the Minimax, well, the result that we are going to be getting is not as high as it could be if everything was ideal and nature was kind of helping us as well, in which case will be a max-max problem. Very good for us, but not very interesting to study. Okay. So max is max. Right, yes. Okay, so Minimax, much more interesting problem to study. And then if, say, that robot first plays first, we should be writing things like this. Okay, so this is what we mean. Robot plays first here. It takes an action. In this case, it's taking maximum action that it could get, right? And see this little variable here. If reward is basically depends on a pair of inputs, both actions from the agent and from nature. One of them is specified at this maximization, and then the other is specified on a second stage, where nature is taking, is deciding, is taking some action, right? And basically what we need to do is solve this Minimax problem. Okay, so, well, this is going to give some value. It's not going to be overall max, we know, but it's going to be some value. And solving this means, this is the definition of Minimax. If we reverse this, you might find also this in the literature, maximin problems, right? In this case, let's say the minimization player plays first, and then comes the second agent, right? But we are mostly just interested in Minimax because the other is equivalent, right? You just need to change things a little bit. Okay, so it looks scary. First, maximization, then minimization, and actually, well, we'll discuss a little bit how to solve things like this. Let me talk now about the second approach, which is the probabilistic model. And I'm going to give here also like some motivations, right? We assume, and this is also a very strong assumption, that we have enough data, right, to reliably calculate this distribution. I was saying that calculating this distribution, usually it's a very complicated problem. Why? Because these distributions, well, everyone is familiar with what, I'm saying distribution, but in fact this is a probability density function, and in this case here what we have is, well, I'm just noting it this way with capital P. It's familiar, right? For most of you, it should be, more or less. Okay. So, we have collected this data. We at least have a prior. It might not be the best one. Maybe it's approximated, but at least we have something to start with. And in this case, what nature does, it's just applying a randomized strategy. So why is this? Because we didn't see clearly if there was a reasoning. We didn't see clearly that it was always mean, that it was always worst case. We saw that sometimes it was raining when we have the umbrella, and it was other times raining when we didn't have. So there was not a clear pattern all the time. Therefore, there was a randomized strategy. This is the best thing we can do, just observe and then collect data. We will not discuss too much on how to get this data, by the way. We will assume that it is, and for now it's okay. But maybe modeling modeling, yes, of this distribution could also be like part of the problem. Very, very important one, by the way. Okay, so now we have this. We know how nature is going to behave, more or less. And then the problem becomes, instead of Minimax, what we are doing is expected case analysis, right, or Expectimax. I took this from Roosevelt book, right? So, yes, they are just calling this problem, and the other was Minimax, like very compact term. And with this, we know exactly what we are referring to. So, how is this going to look like? We have our maximization. This hasn't changed. Okay, this one we still are in control. I mean, you could be random decision makers, right? In this case, what you have is a stochastic policy or a stochastic decision making. That's also possible. Maybe you cannot decide what to do. But for now, let's say that we can choose. We are going to choose max, whatever is best. And then what nature is going to be doing is rolling the dice, letting randomness happen. We don't know. Okay, we cannot know for sure. But what we know is that from all possible results, we can average. We can calculate the expectation. And this is what is indicated here. This is the mathematical expectation with respect to the action theta, that was nature's ones. And then what we have is expected value. Right? From this, we will choose our max. Okay, so far now we started talking about games and all this, but we are just getting back into probabilities and random variables, right? So if someone, I think everyone is familiar with, I already asked, right? Random variables, all this. Okay, but if not, please, I can give like explanation now and then, because this is just for understanding what's going on. Okay, so the definition for discrete variables, in this case our action space is discrete, it has a limited, I'm not sure, but it's a discrete action space. We can write this as summation, right? So what we are doing is just the expectation is just averaging weighted by how likely each of these actions is. We are averaging the rewards, right? So this is what it's doing. Simplest thing is, okay, you assign to all of them equal probability, and then we know what how averaging looks like. But in case that the distribution is different, right? So you have parts where have like higher values versus others, then we need to go over this process. Okay, so let's see this in one example. Okay, so if we go to the non-deterministic case. So in this case, min max, right? It was written like this. Yes. Okay, so let's say that we choose an action. Okay, okay, it's the same example that I showed before. We are going to show exactly. Okay, let me write it like this. Okay, I'm just going to write here what are the okay, how can I write this on a nice way? Okay, yes, let's do this. Let's just try to solve it this way. Assume that we execute action 1. Okay, so if we execute this, what is nature going to do? It's going to choose just -1. Okay, the same happens for this. It's going to choose -2, and here it's going to choose -1. Okay, so now we know what's going to happen if we execute each of the actions, right? And then what we want is basically from all these values, all these potential values, I'm writing here the vector, right? But we want to find what is going to be the maximum for us. And in this case, well, it's going to be this, right? Or this. Okay, probably this one on a table is not very interesting, but you get the idea of min-max. The second one is more interesting, so it's the probabilistic case. And in this case, what we need to do is we need to calculate the expectation of this reward that depends on u and depends on theta. Okay? And from this, yes, we are going to find max. Okay, I think, yes, this one we can write it this way. So I'm just going to write what is the expectation of each of these things, right? Okay, I need help. You will help me. How am I going to calculate the expectation of these 3 values, right? So remember here that u is not considered, and we need to swipe over variables of theta. Okay, so the variable here that we have is theta. Okay, so let me go here. In the definition, what we'll have is several values of theta, and what we are going to be doing is calculating each of these values for each of the actions ui. Okay, so that means that we are going to fix action we take, and then we are going to see what is the expected value for each of them. Okay, so let's start with the first one. Expectation, okay, let me put it this way, with respect to u1. Okay, so we need to calculate the expected value of this thing. I don't know what the probabilities are, but let's say that they are equiprobable. Is that okay? They have the same probability of happening. So in this case, the expectation is just going to be sum of all of them, and then we divide by number of elements. Okay? So what we have here is 1 minus 1, 0. So we have 0 divided by 3, 0. Let's do the same thing here, right? We have minus 1, 2, and minus 2, right? So that means that summation is minus 1 divided by 3. Okay? I'm just doing summations. Yes. What is this thing? 2/3. Thank you. Oh, here. So these are the expected values, assuming that we take each of the actions. We know how nature is going to behave, right? Because it's a probabilistic process. So given these expected values, which action would you take? The third. Exactly. So if we do max of this, this is going to be 2/3, right? So if you choose this one, on average, it's going to give you 0. Okay. If you choose this one, it's going to give you minus third. Still, U1 is going to be better. But if we choose U3, just on average, should be better, right? Because the value is 2/3. Okay? So we need to rely on the statistics. If you change something on the statistics, all this table would be different. But just for you to gather the idea, it's as simple as this. It's just now putting like formulas that we were discussing into the table and seeing, well, what it means to choose. Right? When we have these kind of things, like what is the, for all my actions, what is the expected thing that it should happen? When you have things like so clear as this, then it's kind of easy to decide, right? So this is, well. Okay, good. The example is clear, right? Oh, yes. Yes. Real life, yes. Yes, exactly. If you are talking about this process as a involved process, I understand, right? So when you have a distribution, it could be a continuous distribution. I was here just presenting these 3 actions, which is a discrete state space, but you are right. If you calculate this, it might be a continuous space. You can, as always, discretize, and then you're going to have some problems, and then have your, maybe you cannot discretize because the action space is so huge and multidimensional that does not allow you to discretize, in which case you will have the problem. You might approximate this with a family of distributions. Things to do, there's many things to do, right? But the very basic ones is that, yes, once you have the distribution, then calculating expectation, and with this, you have information, you have an informed way of doing your decision. This is the whole motivation of the slides that we have discussed so far. Okay, so it can get more complicated, but if all of you are with me here on, okay, we've seen a little bit what this table looks like, what is minimax, what is expecting max, I think then we can move on to other things. Okay, we are good. Okay, let's discuss a little bit about other models for nature because, well, Is this the only way that exists, either worst case or simply expected cases? Well, let's say that worst case indicates a perfect rationale behind. So worst case is like this evil nature that is just going to make whatever is possible, well, to get you less reward, right? In this case, this is an ideal rational agent. Or for instance, if you are playing a game against another person, both of you want to win. Okay, so let's call now, instead of nature, we call the other player that you don't know what they are thinking about. So there's some rationale. Both of them want to win. It's not that your player that you're playing against doesn't want to win. Right? The probabilistic case assumes that the expected value is correct. So again, this is a strong assumption. And well, this could lead to some issues. For instance, you could have a height cost on unlikely events, like for instance, collisions on robots, right? And this kind of thing sometimes might give you a correct idea on average, but still you might collide in terms of now obstacles that we are talking about, right? Because things are very unlikely, but still have height cost. So sometimes averages, well, they are tricky. Okay, is there something in between? It's either like so naive that you just take a distribution, you apply it, and then the other option is having worst case. Well, this is the discussion that we have now. We could also be defining utility functions, right? Or we could be defining risk functions. It's just a way of weighting rewards with their likelihood, okay? So this kind of solves some of the problems, still not all of them. Utility functions, these are complicated to formulate. You could be learning like a metric space for utility functions if you want, right? If you have examples of episodes of things having played. But in general, let's say that this is simply a little more precise way of capturing some behaviors that expectation is not taking. And the second one, that this is very, very interesting, is noisy rational. I think that it's interesting because we are noisy rational. We mean people. Why? It's not because we are irrational, right? So there's always some motivation for us to take decisions. But sometimes you don't know what they are. Maybe you have incomplete information. And that means that some problems, you cannot really assume that there's full rationality behind. Even though this sounds a little bit, I'm not saying that people don't think about decisions. What I'm saying is that sometimes maybe the reasons are not rational according to some cost function. Maybe they have another cost function. This is another way of expressing it. Or maybe there's noise. We don't know. But the reality, and if you go and see neuroscience and other fields, they don't really assume, or even robot interaction, they cannot really assume full rationale behind, because sometimes, yes, there's some things missing. So this is a little bit in between. It's not going to be, full rational. Remember, this was Minimax. You assume that worst case, the other agent is going to take best or worst for you and best for the other. But maybe it's a little bit in between. There's going to be some deliberative process, but not worst case, okay? So there's things in between. You should know about this. But the most representative ones, as we have discussed, are non-deterministic and probabilistic. Okay. Okay, let's do a little break, 5 minutes, and then we'll get back to explaining what. Okay, let's get back. Now we have defined all these games, hopefully these two approaches to model nature, right? And what we're just going to be discussing is variance over this and how to make these games a little bit more complicated. We'll see later that solving these games is a planning problem. Right? Okay, another concept that people, instead of just talking about cost, they talk about regret. Okay, so what is regret? Regret, informally defining it, It's this feeling of you taking not the most optimal decision, right? It's kind of this gap between what is the best optimal decision you could ever take and whatever you did, right? For instance, what is the regret of buying your lottery and not winning it? A lot, right? But, well, lots of millions. But for some problems, it makes sense. For others, depends a little bit, right? Once you calculate the regret, you can solve the problems as we were just saying, doing min-max or expecting max. More formally, regret is this, right? Is the cost that you could have saved by picking a different action, right? So in this case, what we see is that this is the best possible action that you could be taking, right? This is the best thing you could be taking, and this is what you took. This is what you actually took, okay? So this difference between the two rewards that you are getting is sometimes, well, it's known as regret. So how can you use this? Same as with rewards. You just go, substitute everything, and you can do the same things that we were talking. Min-max and expecting max and, well, many other things. Okay, another very interesting way of thinking is how can we make use of observations, right? We were saying before that there's this nature that just has some statistics and you just randomly sample you draw one sample from this distribution. So this is true, but it's not always as blind or as naive as this, right? Sometimes, yes, you might have a distribution, but in this case, imagine that, for instance, there's a sensor providing information. You have a little bit of information in addition to your distribution. So that means that your distribution can change. And more formally, what this means is that you are going to have a condition distribution, right? So nature is just going to have a little more information as well. How does this look like? Well, in terms of the min-max, nothing changes, right? In terms of the, yes, on the expectation that we calculate on the expecting max, what we have is that there's a distribution on the actions that is going to depend on some observations. So that's why we are denoting this Z. Right? These are observations that are out there, and, well, they are going to change things a little bit. Right? So this is going to be a little more informed, maybe a little more accurate. Well, we don't know, that depends, but this is just a way of denoting this. If this is true, if there's no relation between the two, we could be saying that these two variables are independent, right? So, okay, how can I write this? Well, let's say that they are okay, I need to check this, but I think the term would be like these two random variables, assuming that Z is also a random variable, although here it's conditioning. They are conditionally independent. Okay, so conditioning between these is not changing this distribution. I'm not saying that they are independent, but they are conditionally independent. Okay, this might be the case, but usually, well, if you have this distribution, it's for something. Okay, another example of decision making, right? This is something that I'm sure that most of you have seen around, is this problem of classification, right? So far we have talked about how to get from point A to point B, right? But an alternative is to think that classification is also a decision-making problem, okay? So what it means, you have some state variables, like this image, okay? Whatever. And then the problem is you need to decide, you need to put a label into this image. What is this? Is this a cat or is this a dog? Maybe it's not so easy to decide. Maybe your algorithm gets fooled by mask, or maybe there's other things. But still, this is a decision-making process where you are going to get a reward if you do this correctly, or negative cost if you do this incorrectly. The question then is, what is nature doing? Right? Okay, so you can consider that nature is just adding some noise here, it's kind of perturbing things. We don't have the canonical representation on the image, right? So there's a lot of noise here, and in this case, yes, we could think that this is a probabilistic problem. All these approaches with adversarial approaches are kind of trying to not assume this naiveness of nature of just being a probabilistic process, but you just go on the other direction of your optimization, right? You try to make adversarial changes to the image such that you get then incorrect labels on the outside. Okay, so nature definitely is there, and the problem to some extent could be seen as a decision making. This is one of the most basic problems in machine learning as well, so I'm not saying that this is a planning problem, but we can think about this as such, right? Okay, now that we have discussed a little bit also this distinction between simultaneous and nature knows, or the other player knows, I think we can define sequential decision making. So far, as I said, we were only talking about length one plan. It means you take an action and that's it. You either take it simultaneously or you take in turns, right, one after the other. But what if now we can consider just a sequence of actions? What if the game just goes over for not a single action, but several of them? We don't know. So this could also be true for games and for many processes going on, right? Sometimes it's not just a single action that you take and then you have a result. Maybe it's a sequence of them, right? And then makes the problem more complicated. We'll see. Again, more formally, we could be saying that our action space is now a sequence of actions. Well, the same for nature and for the other agents. We have just this sequence of actions. And then if we put everything together, what we have is this kind of long min-max replicated multiple times. Okay, and if you're not sweating by now, you should, because the problem has just turned out to be very complicated. Even for 3 action spaces, as we were saying, imagine what is the action space of this sequence, right? What we have here is that for a single action, the dimension of the actions were 3. This was on the example, right? So now what we have is just the Cartesian product of all these spaces. So in total, each of these elements is going to be a combination of each of the actions. So you can imagine, for 2 we have 3 by 3, and so on, right? So basically we have here exponential number of actions, a lot of them. So you want to solve this. If you want to do this properly, then you should be taking each of these combinations, put them together with the actions, and then calculating what is the minimax of this. This exploration only of the action spaces is huge, right? Definitely there's no way for us to solve this properly. So games are complex, we know, right? So there's a lot of actions you can take, other actions that the other player takes, and if you have multiple turns, this is what makes some of these problems very complicated. Okay, so there's hope. I'm going to explain a little bit, because it's not exactly like this, that we need to do exhaustive search over all combinations of actions, but actually what we are going to see is that we can define all these sequential games as trees. Okay, so remember, a tree, well, it's basically nodes that have a unique parent. You cannot have two parents. So if something looks like this is incorrect, right? Okay, so how is this going to solve? How is this going to help us? How is this useful at all, right? So instead of just being a pure combinatorial problem where we have a large space, a large action space versus another action space of nature, and we are trying to get the min-max of this solution, instead of this, what we could be doing is represent this game sequentially with a tree representation. Okay, so what we do is we build graph edges as we were searching. I'm going to give like this example. Okay, let's say that we start here at A. Okay, so we are at A. Okay, let's see. I have this action that is taking us to A again. Okay, and it has cost 2. And I have this other action that is taking us to B. Okay? You see this. And this has, well, probably let's forget about cost. Now, this is the first action. Let's assume that in this game, first agent moves and then the second agent moves. Right? So let's say that we are just, moving is changing this state. Okay, so we only have one state. X is either of these guys. Right? And the agents, what they are trying to do, imagine each of them just moving one piece. Like, oh, it goes to A, now I'm going to move it to B, I'm going to move it to whatever. Okay, so the next position is going to be like this. A now could be doing the same. It could get a get in A, or it could go to B. And the interesting thing is that B, it only has one action that is taking you to C. Okay, so what I'm doing is representing this kind of sequence, and yes, so this was action 1, and let's say that this is action 1 from nature. So these are all the possible actions so far with this game of only nature and the robot that could take us to A, B, and C. These three states are the only ones possible. Yes? Yes, you are right. From B we can reach D. Very good, very good. So what we have now is a tree, only of two actions. Yes, we have a question there. Yes. So I'm going to repeat the question for the... you are saying that trees shouldn't have cycles, and if they have, then this is not a tree. You are correct. But take a look. One thing is the graph, having clicks here, and the second is the tree representation that results from this. And you are going to see in a moment that although the tree is well built, it doesn't have loops or other things that are going to be bad. We are going to see that there's a structure that is going to be repeating, making the number of elements massive. Okay, so let me do it. You will see. Let's execute now next action, U3. I'm going to go like this. So here you can go to A and you can go to B. This is the main problem. So you see the tree is just replicating the same structure over and over and over again. There's no way for us. Why? Because, well, this is just what it's possible, right? And because we are doing this exhaustive search over min-max, well, exhaustive. In this example, we'll see that there's no way to avoid this. B, again, it's going to happen the same thing, right? So it's going to come to C and it's going to come to D. And now we have these two new nodes, right? So in these two new nodes, we can either go to A, we can either go to D, right? And in D, we can go to E, and we can go to C. Okay? So we see that this structure repeats over and over again. We see the same nodes, there's only few limited actions, and at the end, well, if you keep doing this for enough depth, you will see that the number of elements, the number of leaves, if you want, or nodes that creates in the tree is going to be enormous. We only have 4 states here, right? But the tree that is resultant of considering every possible option in the game is gigantic. How can we do this? Well, if you can solve this exhaustively, there's no need for you to think too much. You just put it on a program, go away, and maybe after some hours you have your solution. If you have a problem that does not allow this kind of brute force for combinatorial problems, then we need to think a little bit more. And this is, well, some topic that we will discuss like in a couple of slides. Okay, so now this is another game. I just took this from Laval's book. But this is a little bit the same idea. We have 2 actions, left and right, and in this case we have 2 actors. You see that at the end the number of elements is huge, right? Maybe the graph explaining this game is very, very small. It only has like 2 actions, so that means that there's going to be 2 edges, and I'm not sure how many states, but, well, I don't know. The tree, on the other hand, just grows very, very quickly. Right. So why? Because properly, when we have developed the tree to all its elements, it's going to be all possible combinations. So it's really like a large numbers. This is, well, you know about combinatorials that number of elements is going to be exponential, right? So it's just going to grow very quickly. Still, well, with dimensions, number of elements, and all these things on the actions. Still, if we want just to calculate what is the min-max of this problem, trees are a great search for us for doing this. Why? Because, well, we'll see that actually the tree is just a tool, and we don't really need to calculate everything. So this is what I want to discuss now. And if we have a tree, we can do graph search. Right? So we know at the end, let's say that you decide that, okay, look, for all these things, what you want to choose is, I don't know, this thing. What is your plan? Backtrace, right? Problem set 2. Problem set 1 also. Once you have a solution, you know its parent, you just backtrace things. So here you just go, and then you calculate whatever decisions were made. Okay? So tree also allows you to have like this level of, well, it gives you a lot of information on then later how to apply this. And remember that this is a sequence of actions. Okay, so let's just give a little bit big picture about this. Today we will discuss 2 main techniques. There's many more. This could be perfectly a course, right? So what I'm doing is just presenting the content today very informally. We start talking about umbrellas and rain, and then now we are getting into more details. But if you want to go deeper in this topic, there's many other things. And 2 main techniques are going to be explained, right? The first one is for these Minimax plans. That means that games or things like that where you have a rational agent at the other side, just trying to win, if you want. Here, a very famous algorithm is Alphabeta Pruning. So it's some sort of exhaustive search, you will see, but we are going to cut the tree. We are going to prune the tree. So the idea is you don't need to see everything. There's a point where this option is bad. So this is what Alphabeta Pruning is doing. Well, this is about complexity that we were discussing. And the second example is for probabilistic examples, where we are modeling nature as a probabilistic agent. We will study Monte-Carlo tree search, right? So if you know about this is a very popular technique. We are going to explain today a little bit how it works. In next lecture, we will continue with this probabilistic approach. So next lecture, we will be doing more about probabilistic, Markov decision process, and other, I think, basic concepts. Again, this is more the introduction. Yes, let's say that there's also a way for us to solve these minimax problems or expecting max also using dynamic programming. So this is another option that is available. For now, the most common ones are, or at least the ones that the AI community was more interested, is minimax games, where you cannot really use dynamic programming. You need to go and search exhaustively. So Alphabeta Pruning was the solution. Okay. Okay, so very briefly, I'm going to give the 5-minute introduction to Alphabeta Pruning. So this only works if we have small state spaces and sequences. Why? Because minimax games, it's not possible to solve them approximately. Okay, so we need to do some exhaustive search at some point. And we'll see what is the compromise that this algorithm is doing, right? But still, there's going to be this is going to be the requirement for us to visit many sequences on the game, right? So there's some limitations. That's what I want to say. That Alphabeta Pruning is going to work well, but there's some limits on the dimensions that it can handle. Yes. So for larger spaces, well, I think you need to take other considerations. So that depends. Definitely for larger spaces, the exhaustive search is going to be very complicated. Imagine a plan with infinite number of elements or very large one. It's going to take a long time. Sometimes you have to do this, and then, I don't know, you just run enough CPU power, but usually it's better to take considerations, right, to solve the problem. Okay, so the solution and the whole idea on how this is, why this is working well. We want to be more selective on how we explore, right? So that means that once we are creating the tree, there's going to be parts of the tree that has cost that is very bad, either for one player or for the other player, right? Either if it's because very low and you don't want to keep exploring these options, right? They are like, definitely it's going to be bad, so don't keep looking in this direction. It's a bad idea. And the same for the other agent, right? So you don't need to evaluate all leaves. There are solutions that depend on the previous history, and they are not going to get any better, right? So that means that you can prune on the tree some of these solutions, and you don't need to search for everything, right? So it's basically just divide problem where we need some criteria to prune trees, prune the branches, right? It's just that we need to find these criteria. What is the analogy? In lecture 2, you remember that one of the key elements for E star to be so effective was to have a queue that was ordering elements not by their current cost, but their expected cost to get to the goal, right? If you want, this was like cost to go, but with the heuristic, right? Everyone remembers. What is this thing doing? The only thing it's doing is, look, from all elements that you need to visit, let's choose the good ones. Why you want to choose? If you want to get out from that door, why do you need to choose there or other places in this space? If you have a way to rank them, you do this. This is what we did for A star. For Alphabeta Pruning, it's a little bit different. We don't have this notion of space. We don't know what cost is. But what we know is that we have played the game on the tree for some sequences, not all of them. And so far, it doesn't look good. So if you... Okay, let's do it this way. We start playing, we analyze things, we don't know what is the strategy. We get here, and this cost looks very bad. So later, you don't keep expanding this branch, right? So only the most promising ones are going to be expanded. And well, basically, they have guarantees for when you can find a solution and still prune these things, and there's no need for you to look for everything. Okay, so this is just a class of algorithms. Branch and bound, they are used a lot when you have combinatorials. So just appears in many other algorithms. But the idea, I hope it's clear, right? Both players are going to just decide that some parts of the tree are not worth exploring. They should not be putting more elements, more resources there. I didn't explain how, but if you're interested, then we have the material that I described at the beginning. Okay, and well, this is basically an example of what I was saying. So you come here, this tree is not good, you don't keep going, and the same goes here, and at the end you're just going to prune things such that only parts of the tree are going to be developed. So if you keep going for more iterations, only part of the tree is going to be alive, right? You don't need to develop every branch in this breadth fashion, right? Okay. How to summarize this, right? There's the alpha parameter that controls the max value. So this is what I was saying, one of the agents, right? And in this case, is related to the action U. And the beta parameter controls the mean value for nature, okay? If these values are exceed, then the branch is cut, and there's no need to keep exploring, right? So just a little more explanation. If, and this is a guarantee because this is not a guarantee. We don't have here like guarantees of how many nodes need to be explored, right? It could, in the worst case, could be a lot. Yes, but but the number, ideally, the number of nodes that could be reduced is like this. So if before what we had is B is number of actions in U and D is the depth of the game, number of movements. Here, this was the standard min-max with nothing. You just explore all of them, all elements. This is what you get, right? Number of kind of elements multiplied to the power of number of depths that you take. So you can get a little bit of improvement here. So the exponent is still exponential. That's what I'm saying, that you cannot apply this everywhere. So it's still for limited spaces, but still with this you can solve some problems that this just raw approach or the straightforward approach is not good. It's not good at all. This one still can be like a little bit better. Okay, so the algorithm is a little bit better, but again, has limitations. Okay, let's discuss now the second one. This is very, very relevant because, well, lately this has been used in next to other machine learning approaches, right? And this was a very powerful technique to solve the Go challenge, right, some years ago. So if you remember, well, AlphaGo was basically using MCTS inside, although they were learning policies and doing self-training with their own policies. Part of the key of success was that they were also using Monte-Carlo tree search. We'll see some material for that later, but what is the idea? In general, it's not going to be like full combinatorial samples, totally blind, without having any information. No. It's going to combine this precision of the tree search. So the tree search is putting all elements there clearly, but you need to put all of them. So you need to specify all of them in the tree. We are not going to explore all of them, but we will just explore the most promising ones. And now, promising doesn't mean that there's a parameter saying a number, which is usually hard to tune, right? What promising means is that we will see as we sample. As we keep sampling, as we keep playing the game for a limited number of stages, we'll see how the cost evolves. If we see that some actions taken are giving us, on average, good results, or good reward, that's an action that we should keep exploring. If we see that this action is taking us like very bad rewards consistently, then we should not be allocating more resources into the exploration of that part. So at the end, It's going to find optimal decisions just by taking random samples and building the search tree. Okay? I'm going to explain more in detail later, but the idea is a little bit this. So if Alphabeta was pruning branches with some parameters, this one is doing the same. You need probabilistic modeling, by the way, and it's doing as you are exploring, as you are playing the game, right? It's not that at the beginning you don't have anything. So there's no way for you to know at the beginning, but you need enough samples. And also you can control the number of samples. So this is another great advantage of MCTS. Anytime that you stop, that's it. This is your budget. You don't go farther. So what it means is that if you have this budget of samples and you can stop anytime, these are called anytime algorithms. We know that they might not be giving you the right decision, right? Because you haven't really gone into the you haven't really searched exhaustively, right? But we know that the error is going to be bounded. So this is a very good guarantee, right? Bounded depending on the number of samples that has been then or there. And the other good advantage is that it converges. With infinite actions, it converges to the Minimax solution. So this is really great. Okay, so where is this used? This is used in planning problems or sequential games where you have small action spaces. If you have a very large one, it's going to be complicated for you to create a tree that expands. So a lot of actions means like this. This is like this, right? So this is your action space, that is height. What we are discussing here, large action space. What we are discussing here is some actions, limited number of actions, and very deep games, right? So, for instance, Go is one example of this. You have a lot of movements, you don't know what's going on, but then at the end you need to decide only the next action. Okay, so with this kind of characteristics, if we use Alphabeta, we know that we have a high depth. It's gonna not work well. MCTS on the other side, yes, for high depths gives like a better solution. And that's why we are exploring this a little bit and explaining a little bit. Because maybe you find a problem like this, and then you find out that your exhaustive methods are not good enough, even pruning. So, well, MCTS. Okay, so I think I'm just, this I already said. What we do is we choose the most promising node. Then what we do is an expansion step. For this, a child is selected and the node is expanded, right? So after we select, we expand. Does this look familiar? QNew, QRAND from RRT. Okay, it's not the same, but how to expand a tree should be familiar already. Okay, different names, that's also true. And then what this is really new or interesting from this is that then what we do is we simulate. So what does it mean? We'll see in a second. But because we don't have the full result of the game, what we have is what is called a default policy. It could be a very stupid policy calculated from value iteration from your side that you have calculated in problem set 3 or that you will calculate soon. Or it could be a very complicated policy that has been learned after analyzing millions of Go plays, right? So this is what AlphaGo was doing. It doesn't matter. The important thing is that it's very fast. Remember what was the advantage of policies. Policies don't think. You just take an action. You just take a state, right? And it gives you an action, right? This is lecture 5, a little bit of lecture 6. Very, very powerful thing. If we can really obtain this function, this is fantastic because the planning is already solved. Okay, so then planning means you just let it go. You just follow, right? But you need to calculate this first. Okay. Has anyone finished problem set 3? You have. You have implemented the follow policy, right? I mean the... Okay. How was that?
It was easier.
Easy. Yes. Overall, yes, it was easy. Much easier? I can add more things. No, but what I mean is that there was this task when after you calculate the value iteration, for those that who had not started problem set 3, you will see. After you calculate value iteration, you are asked to calculate the policy, actually the optimal policy. And then executing this, it's going to be lookup table, nothing else. Like, okay, you will see, don't worry. And then we have a last step that is called the backup. So what is this thing doing? It's just taking the simulation results and back propagating. Maybe I don't like it too much. Let's say it's just transferring the result of what you get after doing a full in-depth simulation with a policy. So there's no tree. It's only going in deep. And then it's going to update the statistics. Statistics means expected cost so far on the tree. Okay? Okay, high-level description. Let's see this a little bit more in detail. Okay, because I think for this we need examples. As I said, the simulation policy is the result of combining the tree policy, which improves as we sample, and the default policy. So what is this, right? What is this thing? If you start, what you have is a tree policy. The tree policy is everything that is related to here. Okay? If you want, it's everything that is related to the tree that is already there. And here we have statistics. So what do? Here you already have some cost. You might be looking for minimum cost, or maybe it's an stochastic policy. We don't really know. Depends a little bit on you, but the tree is giving you a policy. It's giving you a way of selecting the action. Okay? But it doesn't go on depth. It doesn't go until you solve the problem. It's just solving for some first actions. Like you move, I move, you move, and that's it, right? Maybe a couple of them. So then, what do we do? Then what we do is we expand the tree. Okay, so after we have selected one of the nodes, still, I didn't say how to select this, but you have the idea that you should be kind of playing here the policy or executing policy after analyzing each of these actions. So maybe it's, I don't know, random decision between the 3 actions proportional to what is the reward. Or maybe you just choose max all the time. You just choose max. It doesn't matter for now. You just play with the tree. And then once you have selected your next state that you are going to expand, you just expand it. Okay, so you play it again. And this is the interesting thing that makes all this algorithm work so well. Then what you do is you simulate an environment. It's going to be the default policy. It's going to be not a good policy. It's going to be just something that is giving you information, right? It's better than random policy. Well, sometimes people play here random policies, by the way. So this is also another option. And then what you do is you get until you get a result. For instance, the play ends, or there's no more actions that you can execute. Executing policies is just calling a function all the time. Lookup table, or maybe another kind of way of storing information. And then after you get this result, maybe this result is, yes, you solve it. You were able to win, or you escape from this labyrinth, or I don't know, you plug in your screw in I don't know, building kind of manufacturing station. I don't know. Then you back propagate, or you propagate back, let's call it this way, you propagate back all these states until up to the tree. And everything that has been here affected is just going to update its statistics. So what it means is that you have a new sample, it's going to be a slightly different reward function. Okay, so this is the only thing that it's doing. And that's it. So key thing here is this simulation. Once you reach this point in the tree that you don't know, you just let your default policy run. And with this, you can have depth explore very, very quickly. Okay? And then the other great thing is that you update your result as you go. Okay, let's see a little bit more examples. Okay, so we simulate an episode, the current state. We are going to build a search tree containing the visited state actions. And then, well, I'm not going to go into much detail into this, but you can think about this as, well, mean return. Here, this function reminds Q function, but it's just for, well, consistency later, because you had to implement this in problem set 4, but it's no longer there. So, okay, let's think just about this as a mean function, mean value that you get. You update with number of samples. And then here what we have is, yes, current number of samples, the result, step function, and so on. Okay? So the same elements that I was discussing before. After we finish the search, then we select the current action that is maximum according to the tree. So how is this? Just this. We have updated this Q function that is telling us for this current state, what are the possible values or expected values if we were executing this policy. And you have to think about it that we have executed this many, many times, right? So choosing an action here, it's not just choosing this action. This action then later, well, let's say this one, okay? This action later is being tested here, maybe you do more parts of the tree, right? So all these are contributing to the statistics of this node here. So that means this Q function that is taking x, let's call it x1 and u, okay? So this is being updated. With more samples, it's going to have more information. So we'll know a little bit variants of this, all these things on the tree. If you get to the end of the tree, then okay, then you cannot really do more simulation. And well, let's say that at the end, yes, the only thing you do is you choose the next action. This is the only thing you can do. Why? Because there's going to be a player that later is going to take another action, right? So, well, you will respond and then you will see. Okay. It also has properties of convergence. So with infinite number of samples, we know that this is a utopic requirement, but with infinite number of samples, you might achieve this optimal cost function, and this is a great guarantee for us, right? Okay, so let's analyze a little bit stories of success of MCTS in this game of Go. Well, it appeared on the news, but I think, yes, the kind of world media or world attention was really, really high. This game, well, basically it consists of positioning pieces, right? So you have white pieces and black pieces, and let's say that the game is complicated to analyze. So number of states is higher than chess, number of actions, you could place your chip anywhere, right? So the problem is really complicated from the point of view of dimensionality and combinations you have, and still MCTS was really behaving very well, plus many other things. Okay, I'm going to skip this, and I'm just going to go to the evaluation, right? Just for you to see the algorithm in action. Let's say that what we have here is this position, okay? So this is our state variable at time t. We have chosen this one. So then, well, actually, no. Here we have, from this state, we have these 4 new actions. Okay, so this is the action, this is the second action. Okay. Look very similar. Maybe I'm missing something. Okay, but anyway, the idea is once you execute one of the actions, you simply do the simulation. So if you see here, there's no tree. It's just a straight line. And here what it means is that we are executing the policies, right, over time. And then at the end, we get some result. Maybe we won the match. This one also won the match, and this one didn't win the match. I think here the actions are simply the same. So these three actions are the same. It's just a way to show simulations, right? So this is just simulations of the these three actions and this another new action. Okay, so think about this as kind of evaluation of simulation, right, until we get here. So you execute, and then what you do is you backpropagate. Okay, so then this is going to update the statistics. So let's imagine that we start here. This is the first state. Nothing has done here. You are there. You have your expected value of being, well, you don't know. What you do is you execute your policy until the end. This is the default policy. And then you get a positive reward. So that means that your statistic, this Q function of executing, is going to be 1. Right? And you only have one sample. Let's go over it a second time, okay? And in this second time, we take another action. In this case, this is the tree policy. Here, what we are doing is expanding the tree. And after we expand, then we simulate. And this second result was not so good, okay? So it had 0. And this is an example of propagating back the cost. So you see here we have the new statistics. It's one sample that has been evaluated in this node of the tree, and the result was 0. This, on the other side, has been 2 samples that have run through this node, and the result, one was positive and the other was 0, right? So this is the new expected value that is calculated. We do this again. And then what we get is a new tree, a new node in the tree that we expand. And now the result is 1. This node now, it's 1 over 1, only one sample. This has run 3 samples, and it got 2 positive results and 1 negative result. So you see, we're updating all the time the statistics. This, it didn't participate in this simulation, okay? So that means that you don't update the statistics. If you imagine this, you could be doing this many, many times. You are just growing the tree. But the great thing about this approach is that as you go, you are getting more and more accurate expected values of whatever is the return of your game. So if you want to think about it as a way of exploring, knowing or updating your expected cost as you explore, this is a very powerful idea, because before we didn't have this. We were exploring and then we were saying, oh, this is the best. Here on the other side, we're exploring, we are updating results, and this is going to help us to better explore, right? So it's kind of a circle that everything helps, everything is contributing to. At the end, what you want is to explore efficiently, right? We have discussed that this state space is huge. You are not going to explore everything. So you just want to see the most promising options that you have. Okay, and so on. You just keep doing this. And then, well, the idea is just that. With some examples, you will update these values. And okay. How can we think about MCTS then? It's very selective best first search. It means that as we are updating these values, we are exploring the tree that is more promising. There's also some problems, right? So sometimes you might be kind of biasing into incorrect solutions. So everyone requires here opportunity. So there's ways for compensating for this. But let's say that this explores the most promising states, and this is a very selective best first algorithm. It evaluates states dynamically, right? So dynamic programming was not possible for doing this. You cannot really update the things as you go. Dynamic programming needed to go over all states, and then you update its values, okay? Here, okay, depends on how many runs you will have more or less information. It uses sampling to break the course of dimensionality. And of course, this has limitations, but at least you don't have this problem of higher dimensional states, higher number of steps in your plan, that is going to bring you like huge combination of states that you need to visit. You don't have this here. You just need like this guarantee of eventually, yes, you will find all solutions. You will converge to the optimum. It also works for black box models. It only requires sampling, right? So here you could be putting anything. You don't need to know anything at all. You could be playing with a simulation if you want. You don't know what's going on. You just know the result. So this is great also for evaluating black box systems. And it's computational efficient. It's anytime. That means that you can stop whenever you want, and it's parallelizable. So you could be running like all these simulation events with as many threads as you want. Okay, as I said, there's many follow-ups for improving this value, this expected value that you have. Well, here you have some of them, UCB and UCT. I took this part of this material from David Silver lecture notes. You can check out the link somewhere. With this, you have, I think, a little better idea of what it means, each of the elements on this algorithm, right? But let me put them again. Yeah, these ones. And as I said, I'm going to upload problem set 4 for those that are curious, at least to see what we were asking. It's not asked. You don't have to submit this. But problem set 4 was about implementing MCTS. Okay? How much time it takes? Well, that depends. That depends on the computational budget you have. But I can tell you that if you have a low computational budget, you are going to find solutions that are not good. So it's not really how much time it takes, but it's how much time it takes to find a good solution, something that solves. For instance, problem set 4, it's very similar to problem set 3, a maze environment, where we had 2 agents, parser and evader. And every time, I think it was taking around a second. I think we were taking 1,000 samples to find the solution. So it was relatively fast. Okay, and then you can increase this budget if you want. But because you are playing with samples, you don't have any signal that is telling you, now I have solved it. You only have an expected cost. And then you are going to choose based on this expected cost. So it doesn't solve the problem. That's the other thing. Minimax, after you go through it will give you the solution. This is the solution. If you take this is what the other is going to be taking. This one is more probabilistic approach, right? At the same time, there's going to be an error with respect to the optimal policy. And most of the time, yes, this works better with probabilistic approaches more than non-deterministic. Okay, very good. Then I will see you next Friday. See you.